Clocked sequential circuits are fascinating components in digital electronics, serving as the backbone for many complex systems. These circuits rely on clock signals to synchronize operations, allowing them to maintain a state based on previous inputs. This is crucial for tasks like memory storage, data processing, and even controlling devices. To understand clocked sequential circuits, we need to delve into their structure. At the core, we have flip-flops, which are the basic building blocks. These flip-flops store a single bit of data and change their state based on clock pulses. When the clock signal transitions, the flip-flops read their inputs and update their outputs accordingly. This behavior allows us to create circuits that can remember past states, making them essential for designing systems that require a sequence of operations. Now, let's talk about state reduction and assignments. In designing these circuits, we often encounter a multitude of states, which can complicate the design process. State reduction is a technique used to minimize the number of states in a circuit without losing its functionality. By identifying and merging equivalent states, we can simplify our design, making it more efficient and easier to implement. This process not only saves resources, but also enhances performance. Once we have our reduced state diagram, we move on to assignments. This involves mapping our states to binary values. The goal is to ensure that each state has a unique representation, which is crucial for the circuit to function correctly. Careful consideration during this phase can prevent potential issues down the line, such as glitches or incorrect state transitions. Now, let's put this into practice with a real-world example, a counter circuit. Counters are ubiquitous in digital systems, used in everything from clocks to digital counters in electronics. A simple binary counter can be designed using flip-flops arranged in a specific configuration. Each flip-flop represents a bit, and the output of one flip-flop serves as the clock input for the next. This cascading effect allows the circuit to count in binary, transitioning through states as the clock pulses trigger each flip-flop. When designing our counter, we start with a state diagram that outlines the sequence of states we want to achieve. For a 3-bit counter, we have 8 states, from 000 to 111. Using state reduction, we confirm that all states are necessary for our counting function. Next, we assign binary values to these states, ensuring that each state is uniquely represented. Once the design is complete, we can implement it using various components, such as integrated circuits or programmable logic devices. The beauty of these circuits lies in their ability to perform complex tasks with relative simplicity, all while being driven by a clock signal that keeps everything in sync. In summary, clocked sequential circuits are essential for creating systems that require memory and state management. By mastering state reduction and assignments, we can design efficient and effective circuits. The real-world applications, like counters, showcase the practicality of these concepts, proving that with a solid understanding of the fundamentals, we can tackle increasingly complex designs.